MESA Research and Seminar Series. So today we have two presenters. One is Sina, another one. You just Sina, huh?
Okay.
Just one. Okay, so you take a longer time and explain the SOC. All right, let's welcome Sina for his presentation.
Thank you, Dr. Chen. Yeah, good morning, everyone. So today I'm gonna talk about self-optimizing control, and this is gonna be the outline of my talk. First, I'm gonna give some statistics for SOC in literature, as Dr. Chen asked, and then I'm gonna talk about some categories of SOC, because SOC, I mean self-optimizing control, and people have looked at self-optimizing control from different perspectives. So I'm going to talk about that. Then today I'm going to be mainly focused on the SOC that Skogestad actually talked about, and he gave this perspective. And this is the same as Skogestad who we have the textbook for the reference for the course Optimal Control with Dr. Chen, Robust Optimal Control. Then I've been working on a project with Lamb Research regarding RF matching. And we designed a gradient-based feedback control for that, and so I'm going to talk about that and talk about how is it related to self-optimizing control. And then we talked about the general framework for self-optimizing control for process control that I'm going to introduce, and finally some thoughts and ideas regarding the literature that I looked at. So I mainly worked with the ProQuest dissertation and thesis library. So it's digital dissertation library. And I use self-optimizing control keyword. And this actually search for dash and without dash. So it's actually does both. Yeah, it doesn't matter. Dash doesn't matter. So if you look at for all the data, in all the databases, it gives 405 titles, and if you look at only dissertation and thesis, you can find 248 articles. But I mean, yeah, they have databases other than dissertation and thesis, and I looked at all of them too. Also, if you look at some other platforms like IEEE and the Science Direct, these are some statistics here. And you can see, for example, the number of articles in IEEE, it was 57, the total, and number of articles since 2000 is 47. For Science Direct, I mean, you can see that the most of articles comes out after 2000, and I'm going to tell you the reason. But in this database, you can see, I mean, it's kind of distributed the same through the years, not much after 2000. And I think this database, I mean, the search was not so good, because only maybe the first 2 pages was relevant. After that, it wasn't really relevant to the search. But let's talk about the different categories of self-optimizing control in the literature. In older literature, mid-20th century, self-optimizing control has been used as an alternative for adaptive control, and I think they still use it, because let's say we have an optimal controller, and then if you adaptively change the parameters so that you keep it optimal, it's like self-optimizing control by literally. So it really makes sense, and I think people still use self-optimizing control for adaptive optimal control. Then in 2000, Skogestad introduced a new concept for self-optimizing control, which is optimally choosing control variables of the control system such that an acceptable operation is obtained with constant set points for those control variables. We are going to talk about this deeply today. So don't worry about this. I'm going to explain this later. Then in heating, cooling systems, in HVAC, people have been using self-optimizing control to refer to optimization-based control algorithms that do not require models, such as extremum seeking control. In extremum seeking control, without a need for a model, we can do optimal control, and this is what they refer to as self-optimizing control in this context. And also there is another category. It's I think the first paper was Lee in this regard, and then there has been some other people that have used self-optimizing control framework for intelligent machines, or like smart exercise machines. I see it mostly for exercise machines, and this is where self-optimizing control allows for online adjustment of what optimal behavior is for the machine, and then there's an adaptive controller to perform that behavior. So the self-optimizing control is the one that, for example, decides the trajectory for the machine, and then an adaptive controller is going to perform that tracking. So now let's talk about the self-optimizing control introduced by Skogestad at year 2000. It's mainly in regard with chemical processes and chemical plants, and the reason is that it's compatible for the plants like this, where we have a hierarchical structure, that we have a scheduling that's like has a longer time period, and then finally we have some control layers that we typically maybe we are more familiar with it in this group, like controls like PID or something that we do, and that continuously running. But then there are some other processes that decide some set points for these processes to perform. Now, so we can see here the set point of the control variables. So we call the set points CS, are the internal variables that link two layers in a control hierarchy, whereby the upper layer computes the values of CS to be implemented by the lower levels. So the objective is to define mathematically the equality of operation in terms of a scalar cost function to be minimized. And solving the dynamic optimization problem is not really realistic. Again, I'm going to go deeper into this. We are going to clarify this. But let's say this is a plant with a lot of degrees of freedom. And if I want to optimize something, let's say like economic cost, okay? I want to maximize the profit for this plant. Then there's a lot of parameters in this. To obtain an accurate mathematical model and to always optimize it, it's not realistic. So here what we are trying to do is to actually it's the self-optimizing control in this sense is when we can achieve an acceptable loss with constant set point values for the control variables instead of optimizing all the time. So we want to achieve suboptimal performance, but replacing the optimization problem by feedback set point tracking to simplify the implementation. So that's what we are dealing here. I'm still going to try to clarify this. So consider these three control systems. So in all three cases, we are trying to do optimal control. In the first case, this is open loop. So let's say for a plant, we have a model, and then we solve the optimization problem. We find all the degrees of freedom to get the optimal operation. But then, if we have any disturbance, we are going to fail in the closed loop, in the open loop system. And now consider like case C. In this case, we use feedback to see the states of the system. But in this case, we need to do the optimization again and again. Like, for example, similar to model predictive control, or, for example, in data scheduling. And this is not realistic, again, because for those plants, the model is going to be very complicated. There are a lot of parameters. And also, like the computational cost, in addition to achieving a good model, this is not realistic to do this. So that's why this self-optimizing control is based on this structure, where we try to have an optimizer to find some set points for a lower level controller, so that this lower level controller maintains those set points to achieve a performance that is similar to this optimized performance. Not exactly, but similar. Because of that, we are going to have a loss. So again here, in the second controller, we have a steady state optimization layer which computes the optimal set points for the control variables, and a feedback control layer which implements the set points. So to see the context of this, like for example, chemical plants, a very simple example you can see here. This is a distillation plant, and it has 2 degrees of freedom that we can change in this case, in this example, which is like the volume of vapor that we can send in here, and then this is the distillant, what the material that we want to actually purify. So we have a control on the amount of feed on this one, and also the amount of feed on the volume. The other inputs here we consider as disturbance, or things that we cannot change. Now there are some constraints here. The constraints is that we want to achieve some minimum purity on this distillant. So we are purifying, and we want some minimum purity at least to be achieved. So we consider this set point. This is like a set point that we consider as a constraint, and then we have a physical constraint that we cannot have some volume of vapor more than some volume. Then objective is to maximize the profit, P. So the cost function, the minimization, is actually the negative of this profit which we want to maximize. And the profit here is related to the product. So we have 2 products. We have the distillant, and we have a side product, B. And we are gonna have some profit with each of these, and then we are going to have some cost. We have a cost for the feed, for the material that we use, and we have a cost for the energy. Okay, so this is what we are trying to optimize. So this is a economic cost, and so the optimization. If you look at it from the first point of view, to do the optimization is that we need to always solve an optimization problem, where we find the optimal U so that we achieve like optimal profit. In this case, we want to actually find 2 control variables that could be these 2, or could be something different. It could be like this is not unique. So we can choose a control variable that if I keep those variables constant, then I achieve something similar to that optimal operation. Okay, so we are simplifying the problem. We are gonna see a more detailed example. This is just to get the context, and let's look at the formulation here. So we want to solve the following a steady state optimization problem, and again the first papers are only regarding like a steady state self-optimizing control. Later people have developed this method for transients, for so many other cases, but the original paper was on a steady state self-optimizing control. And the main justification is that for those plants, the steady state analysis is that the economic performance is primarily determined by a steady state consideration. And this is subject to this inequality. And we are writing these functions based on U and D. U is all the degrees of freedom that we can change, so we can control. And D are all the degrees of freedom that we cannot control, or we can say disturbances. Okay? And so the constraints for instance, what are the constraints? They could be product specifications. For example, like as we saw before, like we could have some constraints on the material that we have. We could have constraints on physical constraints on how we can change these control variables, and we could have some other types of constraints, as you can see, like maximum temperature. Now, okay, so if this problem has a feasible solution, then we are going to have a U optimal. That for that U optimal, we can achieve a optimal cost function that is a function of the disturbance that we have at the time in the plant. So in the actual operation, that we are trying to achieve using like self-optimizing control. As I said, we are going to get some suboptimal operations. So we are going to have a U, we are going to achieve a U which is going to differ from this U optimal. Because of that, we are going to have a loss. And this is how we define loss. The difference between the cost function that we achieve to the optimal cost function. Okay? Then also here, as I said, like we wrote the equations in terms of U and D. We are more familiar with writing them in terms of states of the system. But here we are assuming that these states are like internal variables that we have actually eliminated them by replacing the variables. So we look at the system as only the degrees of freedom that we can control and degrees of freedom that we cannot control. So the whole point of this concept is to use to actually design or choose some control variables to keep constant. So now, what are the requirements for choosing those control variables? Okay. So as I mentioned, yeah, we are going to have some loss because the operation is going to be suboptimal. So because of that, we are going to have a set point error, which we call it ECS. That's the difference. So C is the control variable that we chose, right? So the set point for that control variable that we design is going to differ from that optimal C, because we are not solving optimal control problem. We are just keeping this C constant, right? So there's a difference between them, and that's why we have a loss. And then we also want to consider the like problems in the implementation of the control. So we want to keep this the control. I mean this CS at CS, but we always see this problem that with any controller we are going to have some errors. So the implementation error we call DC, which is C minus CS. So the C that we achieve minus the set point that we were supposed to achieve. So these are two sources of error. Okay. That makes the final loss that we have. So the overall error will be obtained as like the C that we achieve minus C optimal, which is going to be equal to the addition of these two errors. And please don't confuse DC with disturbance. This is the implementation error, although we look at it as a disturbance here. So the requirements for those control variables that we want to choose. The optimal value should be insensitive to disturbance, meaning that the control variables that we chose and we decide that this like CS is gonna help me achieve that optimal operation. This CS shouldn't be sensitive to different disturbances. So if I have a different disturbance, this CS shouldn't change. Then the second, So the second requirement is that it should be easy to measure and control accurately. So those variables, again, we want to control them, so they should be easy to measure and control. Requirement 3, its value should be sensitive to change in the manipulated variable, right? So we have manipulated. This totally makes sense. I don't think it needs explanation. And final requirement 4, for cases with 2 or more controlled variables, the selected variables should not be closely related, so they should be independent. And finally, all of those mentioned requirements can be combined in a single rule called minimum singular value rule. That is for a linear relationship for small variations. For example, if we can relate the controlled variables to the inputs or to the degrees of freedom with G, then we want to maximize the minimum singular value of G. So, and why does, there's a proof showing that why this actually satisfies all these requirements in the main article, but it's easy to show. So, now, So finally, they provide a stepwise procedure how to implement this, because actually in this paper, in the beginning, they they mentioned that actually this method has been discussed, by other people in the literature before, but the reason that people didn't pay attention to it was that they didn't give good implementation procedure for that. So people ignored it, and the first time, and the reason that I told you, like, we have a lot of papers after the year 2000, because in year 2000, the SOC guested, introduced this, and after that, so many people paid attention to this. And so many papers came out on this topic. So this is like the stepwise procedure that they give. So the first step is just to determine the degrees of freedom. We want to see what are those U's, and they should be independent. But this is not a unique set. It could be like different variables. Then we want to determine what is the cost function and what are the constraints on those cost functions. The constraints here are not only the constraints. We want to also we want to determine the bounds of, like, for example, those implementation errors, the bounds of all the disturbance that we have. We want to know those bounds in this case. Then the step 3 is that identify the most important disturbances. Oh, this is the step 3 that I mentioned in there. So, again, those may be caused by errors, that uncertainties in the model, or like as I mentioned, the implementation error. Step 4 is that we want to solve that optimization problem once. We do it offline, okay? We don't have to do it all the time. We solve it once, and we find the optimal values for those control variables in the nominal operation. So nominal operation is that when, for example, we consider nominal operation for those disturbances, let's say in the middle of the range for those disturbances, we assume as nominal. So we want to solve this once, find those optimal values for those control variables. And then, why do we need that? We need this for the next step that I'm gonna, for the step 6 and 7 that I'm gonna say. So step 5 is to identify the candidate control variables, and for to identify these, we had those 4 requirements. Okay, so. And we have also another thing. The main thing is that we want to choose. The candidates are the variables that we can control. Okay, this is the main thing. And then after that, we are gonna go and check those 4 requirements to see which set is better. And so step 6 is evaluation of loss. So we find those optimal values for control variables, because we want to, for different disturbances, the worst case scenario for the disturbances, we want to find the loss when we keep those control variables constant. Okay, so we are going to actually see this in the example. The thing is that we decide the set points for those control variables, and then we calculate the loss for the worst case scenario of the disturbances for all those different set of candidates control variables. And by comparing the the mean value of loss for different set of control variables, we choose which candidate is the good control variable. So basically, as I said, we have a suboptimal operation, but we want to minimize this loss, the difference between optimal operation and what we achieve. So we choose a set that gives us this least value of loss. Okay. So the further analysis and selection is that based on this analysis that we did here, actually we can even modify based on the behavior that we see here. We can modify those sets of variables, and we can actually choose those sets. So here we give an example again, and in this example we follow that procedure that I explained here. Now consider a stir tank reactor. So in this stir tank reactor, we basically have 2 chemical reactions happening. where A like goes to B and B goes to C, but so the final product is C, B is obtained in between, okay? And this is like the steady state like material balance equation. So this is like the dynamic equation of the system. And here, like, these are the mole fractions, Zi and Xi are mole fractions in the feed. We don't need to know the chemical stuff in it. What we need to do to know is from the control perspective. In this case, we only have 1 degree of freedom, and that degree of freedom is reactor holdup. So here we have a feed to reactor. In this example, we assume that feed is fixed, so we cannot control that. But the holdup, I guess, is like how much, I mean, maybe we decide how much we have like output, so how much we keep in the tank is the only degrees of freedom in this case. And then, so the nominal conditions are like feed, again, the feed, that feed is constant, and that feed contains A and C. So basically we have this constraint, or we have this nominal condition for here, and then we have like these mole fractions for A, and also we know the feed is 1 mole per second. So these are the nominal disturbances. But we have a range, so in here actually they give like they define a disturbance. They say like the feed rate could be reduced by 30% as a disturbance. The feed fraction of A can be reduced from 0.8 to 0.6. It could be increased to 1 to 10, yeah. And then, so these disturbances that you can see here could happen. So this is nominal operation, but these are like the changes that could happen. So the first step is to see what degrees of freedom we have. I already talked about it. This is the reactor holdup. M is the only degrees of freedom, and we don't have. So in this case, we talk about constraints here. So the cost function here is that. So the objective is to we want to maximize the concentration of B. So as I said, B is the product that happens in the middle, and we want to have the maximum concentration that we can achieve for B. And in this figure, you can see this is that cost function here. This is so negative of this concentration. We can see there's a minimum here. So we want to achieve this this point. Okay. And the constraints there's no constraints on the system. The only constraint is a physical constraint that the mole fraction should be positive. The hold-up should be positive. And then step 4 is the optimization. So the optimization here, so we need to solve this optimization problem once for the nominal condition. The nominal condition, we knew that the hold-up was 1. These are like, when we solved the optimization problem, we figured that the optimal degree of freedom is going to be 1. So at hold-up equal to 1 mole, we can maximize this, minimize this, and these are other variables that we have, other variables in the optimal condition. Okay. And and in step 5, we introduced the candidate control variables. So how did they choose these control variables? This is what they say. These are the available measurements in the reactor. Okay, and for example, this equation that you can see, this is actually associated with a temperature that they can measure. This is associated with another temperature that they can measure. So these are all available measurements that they choose as the candidate control variables. We need to identify. Then the next step is to actually identify the implementation error. So here they make some assumptions here. For example, they assume that the implementation error is mainly due to the measurement errors, and that the measurement error is 10% for hold-up, and like the feed rate, it's 5% for mole fraction. So based on the measurement error, they come up with the worst case implementation error possible. And in last step is to actually evaluate the loss. So how do we evaluate the loss? We actually do the self-optimizing control. We use one of these candidates. We keep it constant. What is the set point? The set point is the results that we find here. Okay. So for example, if I'm choosing this one as candidate, then it means that the set point is 1 mole. So I want to keep it at 1 mole. Then I find the loss when I keep that m at 1, and not only that, I want to add the implementation error to that value. So I don't use 1. I use 1 plus the implementation error, so I use C is equal to that set point plus the implementation error calculated here, plus 10%, so 1.2, okay, 1.1 in this case. And we use this to find the loss, and we do it for each of these candidates. We want to find out what is the minimum loss that we achieve with these candidates. So the last step is that we choose based on the results that we find here. The table here shows the results here. So for each of those candidates that you can see here, so these are different candidates. So sorry, these are different candidates that they choose, and these are for each of those disturbances, because like linear control that we know, we have to give each input separately, then superposition, right? So they give each of those disturbances separately and calculate the loss for each of them. Then they add up and they actually find the average loss for each of these candidates. And they figure that, for example, with this candidate variable, we achieve the minimum loss. And the one that you see, for example, infinity for this one, it means that this is not feasible. So we cannot keep this variable constant. Okay? We cannot achieve the optimal operation with this. So that's actually, I don't know if it was clear. I tried to explain it as clear as I could, but I can answer 2 questions afterwards if you had any questions. So the first papers published with this idea was like, as suggested, first like a conference paper, then a journal paper, the more complete version of this. The conference paper has 113 citation, and this one has 652 citations. And since 2000, Escogested has published around 30 papers around this self-optimizing control idea that he proposed. And some of those interesting titles that he has in those papers is like a new approach to explicit MPC using self-optimizing control. So this is interesting. I can talk about it. If you had question, I don't have a slide for this. I don't go to these ones. Then explicit MPC with output feedback using self-optimizing control. Just to clarify it a little bit, the regular MPC, we solve the optimization problem at each sampling time. The explicit MPC, the idea is to solve the optimization problem offline and then use some mappings like neural networks, for example, like something similar to machine learning neural networks. So instead of solving optimal control, we have a function, we have a mapping that when we give it the states, it gives us the optimal operation. That's explicit MPC. Now they see like the self-optimizing control idea is similar to that idea, and they can actually use self-optimizing control for this. Then dynamic self-optimizing control for unconstrained batch processes. This was interesting to me because I'm working with batch processes in LAM, and then like run-to-run optimization for batch processes, combining self-optimizing control and external seeking control applied to, again, this is for some chemical plants again. And some example of like dissertations, this is the title of like one of the dissertations that have this self-optimizing control in it. And what they did is that they introduced a simple method for implementation of self-optimizing control when we have changing set of active constraints. Here we assume that the constraints are fixed. Yeah. Okay, now I'm gonna go talk about like the project that I'm doing with LAM and why is it related, because I have already like talked about this before. I'm not gonna go through the details a lot. I'm just gonna try to give it as like the minimum way possible because I've talked about this before. So we have a control problem here. This is called impedance matching. So we have a system where we have a load, and this load is changing. This is plasma, so this load is changing, and we know that whenever we feed a load with with some power to achieve maximum, to achieve optimal power delivery to this load, we need to match the input impedance and output impedance. So we put a matching network in between so that we can match the output impedance with the input impedance. So input impedance here is the R0. The objective is to get Zm, the impedance of this whole part, to be equal to R0. Okay, this is the objective, and the control. Actually, this is a two input, two output control problem. Why? In this case, we assume that C2 and L5 are fixed, and we can only change C1 and C3. So these are variable capacitors. They work with some stepper motor. And then we have, why is it two output? We have like one impedance, but impedance is a complex number, so it has imaginary part and real part. So two outputs, or you can say it has magnitude and phase. You can look at it as two outputs. And what you see here is that when we don't achieve this, when we don't have a matched input output impedance, the problem that we are going to see is that we are going to have some of those power that we want to deliver to the system. This is the power set point. Some of it is going to be reflected. So we have a spike of reflected power, but because we are controlling it and we are matching, then that reflected power goes to 0. Okay. And here are the profiles of C1 and C3. They change so that we match the impedance. Okay, and we achieve 0 reflected power. The output impedance, we can like, these are the equations, so we can model this system. We can find the model for this to achieve, like, to formulate Zm in terms of these variables. The only problem here is that this ZL is not known, and it's very complex. You cannot develop a model for that easily. So many people are trying right now to find a good model for the plasma systems. So this ZL is not known. So for now, I just assume that, which is like, I just consider it as general as possible. It is an impedance with real part and an imaginary part. Okay. Then the reflection coefficient that finally actually we can find the measure of reflected power with is computed using this Zm. So Zm, the relation between Zm and input impedance gives us the reflection coefficient. So what did we do here? The conventional controllers was like they ignored the coupling that is present in the system, because this system is very complicated. It's non-linear. It's coupled completely. But they assumed that, for example, they can only relate one of those capacitors to real part and one of those capacitors to imaginary part. And they used two separate PIDs to control those two control variables separately. And that's why they have a problem, and they needed help to actually make their controller better. What we proposed is that what we proposed is a optimal control, and here we just define a cost function, which is a reflection coefficient squared, actually, and we want to minimize this. So we want to make reflection coefficient 0 optimally. And to do that, I'm using gradient-based method. So the input that we provide is a function of derivative of this cost function with respect to C1 and with respect to C3. So we find the descent direction, and then we use that to move the system towards that point. But we don't use exact gradient controller because, again, this is a real system. And there's a lot of problems associated with the gradient method if you want to use it directly. And this is the like control structure that we are using here. To be able to do that, this J is a function of the gamma here. And gamma, I showed that gamma here, you can see, is a function of ZM. ZM is a function of C1, C3, and ZL. And as I said, we don't have a model for this ZL, okay? So our model is not complete. We just consider the general model here. So what we do here is that we actually, at each sampling time, we use the measurements on C1 and C3, and we use the measurements on VI sensor, the voltage and current behind the match, to estimate this load value, load of the plasma at each sampling time. Then when we find these values, then we use it in the model. So we update our cost function, and then we minimize that. So here I show it again. We have a voltage and current sensor. Based on that, we can find, we can compute ZM, and then having ZM, again, just reverse of this equation, I can find, here I have ZM in terms of ZL, I can find ZL in terms of ZM. So here I can find ZL in terms of ZM, so I can find the estimation for ZL. And then finally, I have a cost function in terms of ZL and the measurements on C1 and C3. So this is a very, very complicated mathematical model that I couldn't do this analytically. I did everything in MATLAB. So the proposed control rule is like I show it in the next slide. So again, if I call like partial derivative of J with respect to C1, JC1, and with respect to C3, call it JC3 with negative sign, then this is the control rule that we use, and this is if we use the like simple gradient method. So here, okay, this is, I mean, to explain why I'm doing all of this, but is a little bit complicated. I can explain if you have question later. But what I want to mention here is that to actually come up with the control output at each sampling time, we are measuring the cost and we are comparing it to, this is one of our control parameters that we can change to this. Then we are also like all of the gains here. So this is, for example, one of the gains in this controller. This is one of the gains in this controller, J divided by J. All of the gains are being changed at each sampling time. So it means that the system is adaptive, right? The control system is adaptive. I'm not using a constant gain. This is a gain in this controller, the cost function divided by like threshold. And this is changing at each sampling time when the cost is reduced. So here we have three parameters. We have KC1 and KC3. These are the controller gains for a steady state performance. So as you can see here, I have this condition that you can see here. I have a threshold cost function. So when I achieve, when I get close to the, when I'm far from the optimal point, I use one rule. When I'm close to the optimal point, I use another rule, okay? And when I'm close to the optimal point, I use KC1 and KC3. So these are just for the steady state performance, okay? When we are close to the optimal point. And but what does J threshold do? The cost threshold do? It can be viewed as a parameter to adjust the conservation in stability. Robustness. To explain this, I need to probably use the board, but I'm going to leave it. I mean, if you needed me to talk more, I can do this. Explain this. Now, why is this? So, why is this whole project related to self-optimizing control? It's not related to the self-optimizing control with like in escogested perspective at all. That I explained right now. It's related to self-optimizing control as people have used it like from before. It's like adaptive control, right? Adaptive optimal control. And the point is, one question that I have is that when we know all the control variables in the systems, the subsystems that we want to control, I have a clear objective. I have a clear control variable that I need to control. and I don't need to determine what control variable to control, okay? So in this case, if we are doing an optimal control, what can we do more? The only thing that we can do more is to just do adaptive optimal control, to always change the parameters to keep the optimal behavior going, not to get far from. So I think adaptive optimal control in this sense is the only self-optimizing control that you could do in this type of system. So, but let's move on. So self-optimizing control, the general framework. Here, this is just a in terms of like process control. Again, we want to see now that with all the computational power that we have, with all the sensors that we have right now in today's world, what can we do to improve the process control? And that is a general framework to achieve a self-optimizing control for this process control in this like subsystem level. Is that we need to have an optimal control criterion. So we need to have an optimal control going on in the system. So we want to achieve optimal operation. Again, some systems you just want acceptable performance, but for example, for Lamb research that I'm working with, maybe it's at some time they were okay with some acceptable performance, but as the competition is going up, no, they want to achieve more optimal. Okay, they want to make it optimal. So we want to have optimal control going on. Then after that, we want to have adaptiveness, right? We want to adjust the parameters of the control system and even the model to actually adapt the system so that we keep that optimal operation. And finally, for example, in the process control, most of the time we are dealing with run-to-run processes, some operation that happens again and again, and they do it again and again. So we want to learn from past. So like the disturbances that we have, we don't know. Next time we want to have better idea how to deal with them. And in this case, we want to learn from history of the system operation to update control parameters and even the criterion for the optimality. So this is in like more general way. But here, I mean, there's this is just a general framework. There's nothing new theoretically added here. This is just a general thing here. So some thoughts and ideas about this, like what I went through today. So this self-optimizing control that Escogested actually, in his perspective, I think has a good potential to be implemented in Lamb research, not for the level of control that we are doing, but for like process design in a higher level, in a plant level, okay? Because they also have a lot of parameters. For example, they want to achieve some etch rate that is dependent of so many variables. And I think the process control team this is exactly the problem that they are dealing with, but I don't know if they are using this self-optimizing control or not. So maybe this is an idea, and Dr. Chen, we used to work, if you remember, at some point we were involved in this topic for a little while with Kai. But actually, it needs a lot of background in we need people who know a lot about the whole thing that is going on in lab. It's not so, but that has a potential in that side. Then RF matching control system already meets the first two conditions for the general SOC framework that I talked about here. So in the project that I talked about here, we already have optimal control going. We have the adaptiveness, but here I want to actually add learning optimal initial conditions from run to run, because the initial conditions of the systems could be still optimized. So I want to come up with an algorithm to optimize the initial conditions from run to run, and that's going to meet the third requirement. RF matching with combined capacitor and frequency tuning should provide a good chance for new ideas around self-optimizing control. Now we are just using capacitor tuning to do RF matching. In this case, one idea that they are using is that you can change the frequency of the power input in a very small range, and that could help with the impedance matching. And the dynamics is much faster than capacitor. So it's like coarse and fine tuning type of thing. And because frequency tuning is going to be so fast, I mean, we can use extremum seeking control probably. I think this provides a good platform to try to come up with a like how to translate self-optimizing control in a way that we have something new to say actually. Or then finally, my question again is that in subsystem level control level, where we have clear control variables and objectives, how can we separate self-optimizing control from adaptive optimal control? Is there, I mean, I don't see how we can do more than just adaptive optimal control. And this is something that I have in mind and I'm trying to think about. So finally, if you have questions, I would be happy to explain all those things that I skipped. So feel free. Yeah. Okay, that's it.
Very good. Thank you. So we have pretty good time here to discuss a few things. So first of all, we had some experience about gradient descent method, how to accelerate it. So it's called AGD, okay, accelerated gradient descent. So I understand you tried some accelerated GD methods. So what's your overall impression, especially for the Nesterov method? And so in the industry setting, do they really care about this accelerated GD method? And what kind of potential benefits we may get from it, in addition to being fast?
In addition to being fast?
Yeah, convergence. So.
What I can explain is that, do you have a marker? Sorry.
I can do it.
Sorry, I'm not here anymore. I don't have markers. I think Jairo has some. Yeah. I don't know if I'm going to use it much.
Yeah, so you also did animations about different patterns, but what's the so you have accelerated gradient descent. And next question is at what price?
So right now, this is so what I'm doing here is that, I mean, I can also explain some of the things that, so here we have a 2D system. So let's say I have this is hard to show. So let's say this is a 2D surface where we have actually a minimum here, a global minimum here. Okay, let's say this is something like that. Although I'm not.
Phase portrait. What is your x-axis?
No, this is not phase portrait, but this is, let's say, so let's say I have x-axis and so x and y. So I have C1, I have C3. I don't know. So C3, and then I have the cost function J. Okay. So this cost function and that I'm trying to minimize in the space of C1 and C3. It actually has a minimum, right? Otherwise, I cannot use gradient method. And I have checked this for all the cases. I mean, we have a global minimum here. That's why we can use this gradient method. So what I'm doing here, Dr. Chen, is that if I just do gradient method, so I'm finding the gradient, the descent direction, right? Then we move towards this direction with some speed. This speed is dependent of the slope, right? And also the step size that we choose. The problem is that load, whenever we change the load, that's ZL. So whenever I change this ZL, although the curve still has a global minimum, but this curve changes totally. I mean, the slopes, everything's changed a lot. So the steps that you use, for example, for this case, maybe you decide a step size that is fast enough, it's good. But then when you change ZL, it could be not moving at all because those slopes in terms of like the speed that we want is super slow. So the point is that we need to normalize the speed that we are moving toward the set point. So in this case, using gradient method or accelerated gradient method is not going to change much because the problem is that we need robustness to the change of load. And we don't have it with the regular gradient method. What I did here is that I'm normalizing it. So, for example, here when I'm far from the response, so when I'm far from the optimal point, you can see here that I see which one of these slope is higher than the other one. Okay, so one of them is larger than the other one. Then, for example, if this one is higher slope, then I move C1 with the maximum speed. Okay, I don't care about the slope. I move with the maximum speed all the time. Okay, and then for the second one, I make it in a way that I keep the proportion between these two, so that I keep going in the descent direction, but with the maximum speed. So the problem with the gradient method or accelerated gradient method is going to be this robustness, and you cannot achieve it with the accelerated one. When I used it, how did I use it? I use it in this way. Let's say I did it in like MPC type of control, model predictive control. When instead of at each sampling time just calculating like the descent direction and moving this way, instead of that, what I did is that I used MPC, meaning that at each sampling time, at each point that I use gradient method to completely solve the problem and find the optimal point, then move from this point directly toward this point. Okay? Does that make sense? So this is the MPC. Now to solve this whole problem in one sampling time, I use the accelerated method so that it's like less computationally, or it's faster to achieve, because I mean this to run this, I need to run it for some iterations, right? I want to converge sooner, so I used but I'm not using MPC in this case because
is Vmax how you choose the Vmax?
Vmax is the input by operator. So they have, this is the rate limit on how fast we can move the motors. This is the rate limit of how fast the motors can move.
Vmax is the rate limit?
Yeah, this is the maximum speed that they can move the motors to change C1 and C3.
It's a rate limit?
Yeah, it's the rate of change in your parameter, right? This is the limit on the rate of change that you can in your parameter.
Position servo, then you are giving the speed.
Yeah. So maximum speed that it can move.
Very interesting. Very interesting.
Yeah.
Can you next time ask them how they decide this one and how this is linked to the performance?
I asked Dr. Jung before. I think the reason, I mean, it can go faster, but the reason that they limited it to this number is that they didn't want it to be so harsh. So it's like they put a saturation limit on that. But maybe maybe they did that because the control was not good, and I mean, if it's too harsh and you go in the wrong direction for a while, it's going to be bad. So maybe if we have a good control, feedback control node, maybe they can increase this and even get better performance.
Okay, that needs more investigation.
Okay.
Even in your simulation, you should try different Vmax.
I've done that.
To see how this will affect our performance.
I've done that. Yeah, it directly changed the performance.
Can we use accelerated GD with the constraint on this Vmax?
Yeah.
With this Vmax constraint.
Maybe I should.
When people do optimization, they don't have any rate limit, right? So now you have a rate limit in the real world. So this is a new problem. I don't think in the AGD community people even thought about this. This is a new line of research. Another comment I want to ask is your is your initial state learning. Okay, initial state learning. I think in SOC framework, this initial state learning is totally ignored. Okay.
And let me take notes.
No, I don't think they even started it. I just send you an article I wrote this year. In 1999, 20 years ago. Now we see this is an important problem. Because you already learn in industry setting, people care about the initial state very much. If you ignore that, you are going to have inconsistent.
Oh yeah, I see. So initial state learning for self-optimizing control.
Yeah. So please do that. Let me check it.